When chemists carry out a reaction, they're never going to be 100% efficient. They won't get every single molecule of reactant to go to the product side of the reaction. So the way they get an idea of how well the reaction went is by calculating a percentage yield. So far in our calculations, we have been determining what's called a theoretical yield. So that's the maximum amount of product that you could expect based on your stoichiometry calculations. But then when you actually do the reaction, you probably are going to get less than that. And the amount of product that you actually get is called the actual yield. So from those two yields, you can calculate a percentage yield, which is a measure of how successful their preparation of product was. And so the formula for that, percentage yield, is just your actual yield over your theoretical yield times 100%. So it's the same idea as when you calculate a percentage that you get on a test. It's the actual number of marks you got over the theoretical number of marks you got if you'd gotten everything correct times 100%. So let's look at some examples. So according to the stoichiometry calculations, the maximum amount of ammonia that can be produced from 1.00 kilograms of nitrogen gas reacting with excess hydrogen is 1.22 kilograms. When the reaction is carried out, 0.852 kilograms of ammonia is obtained. What is the percent yield of the reaction? And there's the reaction that's happening there. So we're going to calculate the percent yield. We have to figure out what those numbers are, which one is which. So we've got 1 kilogram of nitrogen gas possibly producing 1.22 kilograms. So that's your theoretical yield, that 1.22 kilograms. And then when the reaction is carried out, it's 0.852 kilograms of ammonia is obtained. So that's your actual yield. So for the calculation, those are the two numbers that you need. The 1 kilogram of nitrogen gas isn't relevant to this calculation. So we take the actual yield, we divide by the theoretical yield, times by 100%, and you get 69.8%. So the percentage yield of that reaction was 69.8%. And it doesn't actually matter what the units are for mass, as long as they are the same unit, and they'll cancel out. So that's the calculation for percentage yield, but often with percentage yield questions, you first have to actually calculate the theoretical yield. So let's look at some of those examples. If 45.00 grams of ammonia is produced when 42.00 grams of nitrogen, N2, reacts with excess hydrogen gas, what is the percentage yield of the experiment? So we're going to need the molar mass of ammonia and the molar mass of nitrogen because we're going to need to do a stoichiometry calculation to figure out the theoretical yield of ammonia. The 45 grams that's given in the question is actually the actual yield. So we're not going to use that in our first calculation. We're going to take the 42 grams of nitrogen and figure out what our theoretical yield of ammonia could be. So we'll start with our 42 grams of nitrogen. We'll multiply that by the molar mass of nitrogen. Then we'll use the mole ratio from the balanced chemical equation to figure out the number of moles of ammonia. And then we'll use the molar mass of ammonia to find the mass of ammonia that could be produced, or the theoretical yield. Okay, so our theoretical yield is 51.0835 grams of nitrogen. So keep in mind, we're not done the question yet. So keep a couple extra digits on that number. Now that we have the theoretical yield, we can find the percentage yield. So percentage yield is actual over theoretical times 100%. So remember from the question, the actual was 45.00 grams. We just calculated the theoretical. So we're going to divide those, multiply by 100%, and we get 88.09%. Another example with just a little bit of a different wording. The most common ore of arsenic, FeSAs, can be heated to produce pure arsenic. When 25,000 grams of this ore was processed, 9,530 grams of arsenic was obtained. So what was the percentage yield of arsenic? So in this case, we've got 25,000 grams of the ore, and the actual yield from that was 9,530 grams. So the first thing we need to do is calculate the theoretical yield when we process 25,000 grams of the ore. So we're going to need the molar mass of the ore, which is 162.83 grams per mole. And we're also going to need the molar mass of arsenic so that we can calculate the theoretical yield. So we're going to start with that 25,000 grams, use the molar mass to convert to moles. Then we're going to use the mole ratio, which in this case is just a 1-to-1. And then we're going to use the molar mass of arsenic to get us to the theoretical yield of arsenic. So when you do that calculation, you get 11,502.79 grams of arsenic. Now that we have the theoretical yield, we can calculate the percent yield, remembering to keep a couple extra digits. So percent yield is actual over theoretical times 100%. So 9,530 grams divided by 11,502.79 grams times 100%. We get 82.849%. But if we look back at our calculation, that number 25,000 only had two significant figures. So our actual final answer is going to be that there was a percentage yield of arsenic of 83%. So that's how you calculate the percentage yield. It's actually just really one new step from what we've been doing before, just that extra calculation of the percentage yield. So now we'll look at a little bit of a different problem where we're going to use the percentage yield equation but rearrange it to find the actual yield. So in this example, determine the mass of sodium chloride that would be produced from the reaction between 23 grams of sodium and 37 grams of chlorine if the reaction proceeds with a 67% yield. So we're given the percent yield, and what we're being asked for is how much is actually made. So in order to figure that out, we're going to have to find the theoretical yield. And because we've got information about both reactants, this is also a limiting reactant problem. So for each of those reactants, sodium and chlorine, we're going to calculate how much sodium chloride they could make in theory. So we've got 23 grams of sodium. So we convert that to moles using the molar mass of sodium. Then we're going to use a mole ratio to find out how many moles of sodium chloride could be made. And then we'll use the molar mass of sodium chloride to find out the mass of sodium chloride that could be made if all of the sodium reacted. Then we're going to do a similar calculation for the 37 grams of chlorine. We're going to convert to moles using the molar mass of chlorine. We're going to then convert to the moles of sodium chloride using the mole ratio from the balanced chemical equation, and then use the molar mass of sodium chloride to find the mass of sodium chloride that could be made if all of the chlorine reacted. So we see that sodium would make less sodium chloride, so that means that sodium would be our limiting reactant, and that this would be the theoretical yield. So the most that could be possibly made from this reaction is 58.465 grams of sodium chloride. The question wants to know how much would be produced if there's a 67% yield. So we can find the actual yield by rearranging the percent yield equation, which I've done there. So it's normally actual over theoretical times 100. So we've just moved over the theoretical and the 100. So we can find the actual yield by multiplying the theoretical yield by the percent divided by 100. So we can take our theoretical yield from our calculation times 67 over 100, and we find that if there was a 67% yield, there would be 39.17155 grams created of sodium chloride, but we need to express that to the correct number of significant figures. In this case, our percent yield of 67 only had 2, so our answer can only have 2. So the answer to the question was that 39 grams of sodium chloride would be produced if there was a 67% yield for this reaction.